Kohinoor Arts, Commerce and Science College, Hyderabad. Myself, Sunil Gaundrahote, Assistant Professor, Department of Chemistry. This video is made up of for online teaching for education purpose only. BSc third year, 5th semester, paper number XIV, Sauda, Organic Chemistry, chapter first, Spectroscopy, and this is a part first. There are different parts, first, second, third, like that. This is a part first. BSc third year, chapter first, spectroscopy. What is meant by spectroscopy actually? This spectroscopy used for, this is one type of technique to utilize to analysis the sample, to measure, means whatever may be the sample that we are, for example, water. Why it is called as water? Exactly how there is only the H2O is there in water. That type of search or investigations, for that purpose the spectroscopy is very important. The nuclear magnetic spectroscopy, there in this chapter we are looking here to nuclear magnetic resonance spectroscopy. Nuclear magnetic resonance means, nuclear means there are the atom, in atom there are nucleons, and in that nucleons measure the protons or H1 hydrogen, protons or hydrogens. That is the nuclear magnetic resonance spectroscopy. That is proton magnetic resonance, H1 NMR. The spectroscopy, nuclear shielding and deshielding. In that proton magnetic resonance, we are seen there shielding and deshielding of the peaks in that spectroscopy, and from there this spectroscopy mainly used for the organic molecules. Those molecules are binded to the carbon atoms, mostly the carbon atoms or organic compounds, CH bonds. The chemical shift and molecular structures. It is also here we are seeing the spin splitting and coupling, constant areas of signals, interpretation of PMR spectra of simple organic molecules such as ethyl bromide, ethanol, acetaldehyde, 1,2,2 tribromoethane, ethyl acetate, toluene, acetophenone, or so many organic compounds. The problems pertaining to the structure elucidation of simple organic compounds using UV, IR, NMR, PNMR, PMR, means proton magnetic nuclear resonance spectroscopy techniques, combining and single lambda max using Woodward-Fisher rules. We are calculating the UV spectrum also in another way, and we correlate this data and we are predict the structures. Then spectroscopy. What is meant by spectroscopy? Spectroscopy is the study of the interaction between matter and electromagnetic radiations. The spectroscopy is nothing but the interaction between electromagnetic radiation and that matter or that compound, and we are getting the some signals from that. That is the spectroscopy. In general, the study of the NMR spectroscopy, radio frequency are used. Radiation by nuclei is called as nuclear magnetic resonance. Spectroscopy is a study of how light interact with matter. We can use spectroscopy to determine the structure functional group in organic compound. This is our purpose of this chapter. The method of NMR was first developed by E.M. Purcell and Felix Bloch in 1946. Then nuclear magnetic resonance NMR spectroscopy defined as an analytical chemistry technique used in quality control and research for determining the content and purity of the sample as well as molecular structure. For example, NMR can quantitatively analyze mixture containing known compounds. There is a enantiomers also calculated by NMR spectroscopy. Introductions of nuclear magnetic resonance spectroscopy. NMR is a spectroscopy techniques that detect the energy absorbed by the changes in the nuclear spin state. Nuclear spins means that there is a two spin is there, one is a positive and another one is negative spin is there. The nuclei are composed of proton and neutrons. There are two types of materials are mostly observed in nuclei. There is one is a proton and another one is neutrons. And third one is there is a proton. Protons carry positive charge while neutrons are electrically neutral. Nucleons carry the charge to consider the spin. The spinning of charge on the nuclear axis generating magnetic dipole along the axis of the spin that act as a tiny bar magnet. Means the spinning in many atoms there are charge is there, positive or negative charge. That charge on nuclear axis generating a magnetic dipole means the dip magnetic dipole are applied on that matter that get converted into parallel, horizontal, vertical, like that axis plane may be the plane of that magnetic dipole, or it may be horizontal, or it may be up or down. The dipole along the axis spin that act as a tiny bar magnet. Then the direction of the rotation of that spin, this bar is indicating as a north and south pole is there, and we are applied the magnetic field on it. This is a spinning. This nuclei is spinning when applying the magnetic field, and that get rotate around it. And this is the magnetic field. The spinning proton generate a tiny magnetic field on along sidewise. This is the tiny magnetic field, like the little magnet and angular momentum. The odd atomic number and mass number means which compounds are active spinning protons. There is a having unpaired electrons. Only those molecules are odd atomic number and odd mass number. This is atomic number 179. These are the active nuclei. These are active in PNMR spectroscopy, like this also nitrogen 15 also, or F19 also. The odd atomic number, even mass number. The 17 hydrogen 1, nitrogen 7, these are inactive for for NMR spectroscopy. Odd and even number, odd even number or odd mass number means this is even number and this is odd number. Mass number, atomic number is even 6, 8. This is 13 and 17. But these also C13 are also the, it is one of the C13, this C6H13, this is also used as a C13 NMR spectroscopy. Then which atom are active in NMR and PMR spectrum or PMR spectroscopy? The nuclei having even mass number and even mass number, and even mass number, example 1H2, 7H, 14, 5B10 are the not generate dipole because pair of proton and neutron oppose the spin while the spin 0, and hence these are inactive in NMR spectroscopy. The NMR active atom are the nuclear generating magnetic dipole moments mu, like the example 1H1, 3H3, triton, 6C13, 9F19, 15P31. This is also the active P phosphorus, also this phosphorus 15P31. This is also the active in NMR spectroscopy, or that is the phosphorus spectroscopy, actually phosphorus NMR spectroscopy. For the nucleus having a spin, quantum number is I. These are 2I plus 1 spin state. The two properties of nuclear particle which are important in understanding of NMR spectroscopy are the The two properties of NMR particle which are important in understanding of NMR spectroscopy are: first one is the net spin associated with the proton and neutron, spin associated and distribution of the positive charge on the molecules. The net spin number or spin quantum number I of a particular nucleus can be obtained by adding spin numbers of individual proton and neutron of half each, assuming that neutron cancel only neutrons and proton cancel only protons, because of pairing of spinning in opposite direction. The spin number I have values 0, half, 1, 3 by 2, 5 by 2, and so on. Fourth, if the I is equal to 0, that represent no spin. Means the formula is that 2I plus 1 is equal to 0, or in proportion to, that is no spin. There is a spin is not there. The NMR is mostly concerned with the nucleus spin quantum number I is equal to half. The proton having I is equal to half, which plays an external magnetic field H0, it is start to spin around the nuclear axis and generate another magnetic field. According to the quantum mechanics, there are 2I plus 1, so 2 spin stage plus half and minus half for the protons. Means there are one rotate clockwise or another one anti-clockwise. This is the applied, this is the ground state of the without magnetic field, and this is applied magnetic field. Is energy difference plus half and minus half. Then spinning nuclei magnetic moments. Some elements have the isotopes with nuclei that behave through they were spinning about an axis, much like the Earth. The spinning of charged particle generate a magnetic field along outside of this tiny magnet. As a consequence, the spinning nuclei behave as a through they were tiny bar magnet having a north and south pole. This is without magnetic field, and this is a applied magnetic field at the time. These are get up some direction is state vertical directions. This is rotated clockwise or anti-clockwise. This is after applied magnetic field. The spinning flipping spin protons. Energy required flip the proton from its lower energy state to the alpha spin, means lower energy level spin state, to the higher energy state of beta spin. Beta is higher energy level. In PMR spectrometer, the higher energy is supplied by the electromagnetic radiation in the radio frequency region. Wavelength is near about 10 raised to power 14 angstrom or 10 raised to power 10 micro or 10 raised to power 6 centimeter second. These are the figures. This is the applied magnetic field. This is the ground state. This is the excited state. And after applying energy, the spin getting parallel beta state. It goes to the beta state. The energy difference between two nuclei. Energy difference between two energy level alpha and beta spin state delta E for the proton is given by. Here delta E is equal to H Guy H0 upon 2 pi, where H is the Planck constant, Guy is gyromagnetic ratio or magnetogyre, H0 is applied magnetic field. Gyromagnetic ratio is defined as number of presentations per second per unit field. For proton, gamma is equal to 26750 Gauss per second or 2.6750 Tesla per second. 1 Tesla is equal to 10 to the power 4 Gauss. Del E is equal to h nu. H nu is equal to h upon Guy upon h0 upon 2 pi. Nu is equal to Guy h0 upon 2 pi. H get cancelled here. Then frequency of 40 megahertz is needed as a magnetic field H0 of the 9400 Gauss flip the proton from its alpha spin state to the beta spin state. When the proton are treated with external magnetic field, the magnetic axis of the proton will process about the axis external magnetic field. In the same manner, the gyroscope process under influence of the bar omega 0 is equal to proportional angular velocity, Larmor frequency, that is omega bar omega 0 is equal to Guy h0 from fundamental NMR equations. Nu is equal to Guy h0 upon 2 pi. Then put omega bar omega 0 is equal to Guy 0. Then the equation become nu 2 pi is equal to Guy h0. Then omega 0 is equal to nu 2 pi. Then in PMR, one does not measure all the proton but just those have alpha spin and absorb the energy in flipping to the beta spin. The nuclei with beta spin can also give continuous excitation and relaxation. Types of relaxation: spin relaxation, spin lattice relaxation. Spin relaxation is the energy transferred to the other process nucleus. There is no net loss of energy. NMR get broadened due to the spread of energy. Spin lattice relaxation is here transferred energy to other lattice molecule. Total energy remain constant. Excess of nuclei in lower energy means the state is lower energy. The mechanism of absorption of radio frequency in NMR, the top processing in the earth gravitational field B, the process of the spinning means spin, this nuclei is spinning nucleus resulting from the influence of the applied magnetic field, which are applied magnetic field at the time this is revolving and it make a tiny bar magnet, and there is a certain influence is there from top and down when applied magnetic field. The nuclear magnetic resonance process absorption occurs when nu is equal to omega, where nu is applied radio frequency and omega is angular frequency of precessions. This is h nu is equal to 60 megahertz and omega is equal to 60 megahertz. At that time, this is the applied magnetic field and this is a tiny bar magnet, like it is occur like this, and then absorptions, it make absorption occurs at a plus half to minus half, and this is the instrumentation of NMR. H1 NMR spectrometer consists of the magnetic radio frequency generating and detection device. The sample 5 to 50 milligram means how to prepare the sample for NMRs. Means spectrometer consists of magnet, radio frequency generating and detection of device. There is also the preparation of the samples. The sample is taking near about 5 milligram to 50 milligram to taken in an NMR tube and dissolved in deuterated solvent like CdCl3, D2O, CCl4, DMSO, CD3OD, CD3CO, CD3, etc. to enable only the proton on the sample to the observed. Why these solvents are used, deuterated solvent? Because of for NMR spectroscopy, these are different molecules CdCl3 and that dissolve the compound from DMSO. There is a one peak is there for in the sample in spectrometer means sample. This is a NMR tube actually. In this is a we are adding sample here. These are NMR tube. This NMR tube keeping inside the that magnet up to here, and that record the spectrum. The sample holder, glass tube with, this is sample holder. The glass tube with 8.5 centimeter long, 0.3 centimeter in diameter. The permanent magnet, it is provided homogeneous magnetic field at a 60 to 100 megahertz. Magnetic coil, there is for in instrument there is a magnetic coil. This coil induce magnetic field when current flow through them. Sweep generator, there is a sweep generator to produce the equal amount of magnetic field pass through the sample. Means from the sample there is equal amount of magnetic field pass through this sample. The sweep generator is radio frequency transmitter. One is the radio frequency transmitter. That what is the function of radio frequency transmitter? This is a radio transmitter coil transmitter that produces a short powerful pulse of radio waves. Radio frequency receiver. There is one receiver. Radio receiver is a coil that detect radio frequency emit as a nuclei relax to the lower energy levels. Readout system, the computer that analyzes and record the data. Readout systems, this is actually NMR instrument, and how it is function, it is here. One is sample holder, this is sample tube, this is sample holder here. Then permanent magnetic probe, this is magnetic controller, this is detector. Sweep generator, radio frequency transmitter, radio frequency receiver. Readout systems, readout system is a readout system. And this is receiver here, radio frequency receiver. This is the radio frequency transmitter, this transmit the radio frequency to here. Then we keep the sample here, and then magnetic field applied. This is the radio frequency transmitter. Then this magnetic field goes to the receiver to receive the data and reflect the readout system. Means how, where is the peaks are observed, that is observed on the screen. This is actually, this is a photo of NMR spectroscopy, or this is also used as C13 spectroscopy. This is sample tube, this is magnet, this is detector, this is RF transmitter, this is absorption and reflected into the printer. This is magnetic field, also how much magnetic field I apply, and this absorption from that to overlap that spectrum and make the peaks there. And this is magnetic controller. Then how NMR spectrum are measured on the screen, or where what is the actually a graphical graph the NMR system, how I would like to show, or how it is a sample. Actually there are this as the measured in the part per million, and this is applied magnetic field here, that shown here, and this is the part per million. This scale is part per million, and these are the NMR peaks are there. This is actually the ethanol spectrum. It is a typical ethanol spectrum. This is a triplet, this is like a singlet, this is like a quadrate. Means four signals are there, a quadrate. How it is observed, the magnetic field of Sauda 14,092 Gauss, the frequency of electromagnetic radiation required to flip the proton is 60 megahertz, or mega cycle per second. 1 megahertz is equal to 10 to the power 6 CPS, cycle per second. And actually this is upfield, means near about 0, that is upfield. Shielded zone is there, and downfield is the 0 to 1 2 3 4 5 6 7 8 9 10. It is goes toward on left side, actually goes on left side, that is the downfield and de-shielded. And the shielded zone is, it is near about 0 to near to 0, and higher it is shielded and downfield also. These are the typical spectrum. How it get taking triplet, this is singlet, and this is quadrate. Because of neighboring, it is measure the neighboring protons. Means this, for this carbon the NMR peak spectrum peak is this one, and its neighbor carbon proton is 1 2 3. Because of this neighboring carbon proton, that counted this n plus 1, means 3 plus 1 4, because of that quadrate is there. And for this carbon, this is the signal of this carbon, it is shielded upfield carbon. It is carbon, due to that proton signal is there only in NMR or PMR spectroscopy. This is the, for this carbon there are one carbon is there, and for that carbon there are two peaks is there, two hydrogen is there. Because of that, two plus 1 3, because of that 3 there is a triplet along with this carbon, and one hydrogen along with the OH, because of only single hydrogen is there, because of singlet is there of this oxygen, but actually this is OH group, is hydrogen is there, this is the singlet is there. Various aspects of PMR spectrum. The effective field strength at each proton depends on environmental, such as the electron density around the particular proton, the presence of other neighboring proton. Various aspects of NMR spectrum as follows: the number of signals in the PMR spectrum correspond to the number of sets of equivalent proton in the molecule. In previous example, there are three sets. This is the one set, this is two sets, this environment and this environment is different, because of this is the third set, this is second, this third, means 1 2 and 3, like this sets molecule. The position of signal gives the information about the electromagnetic environment of each set of equivalent protons. The intensity of different signals are proportional to the number of protons in each set. Intensity means that intensity is this intensity. If this is goes above, means there is some similar proton is there, and it get means intensity like this. We are measure intensity like this, and that intensity is higher, the proton value in that peaks is higher. The intensity different signals are proportional to the number of protons in each set. Splitting of each signal into several peaks gives information about the number of neighboring protons. Means that triplet, singlet, triplet, quadret, triplet, quadret, doublet, triplet, quadret, like this, multiplet, like this. Then position of signal in chemical shift. When a molecule placed in magnetic field, electrons of the molecule carrying negative charge. Electron carrying negative charge under the influence of the external magnetic field will circulate, and circulating will generate their own magnetic field. This is magnetic field generated by the circulating electrons, as called as induced magnetic field, which may either reinforce or oppose the applied field. The magnetic momentums of the electrons generally reduce effect of the external field, that is shifted nuclei. The more shielded a nucleus is, the more shielded means shielded, deshielded, more shielded, the smaller the alpha to beta spin gap, because proton is influenced by the external magnetic field and effect of the electron field. This is acetylene molecules. The applied magnetic field, the generating magnetic field along with outside in induced the flow of the electron is like this. This opposite means this direction. The pi system of the alkyne. Induced a local magnetic field. This is around the molecule field pi electron in against the applied field. It requires a greater applied field to bring an acetylenic hydrogen into the resonance. Then circulating the pi electrons of blue, this is the pi electrons, blue ring, current red, and this is the induced magnetic field, reinforce the external magnetic field B0 near the proton, which are the deshielded. These are the deshielded. Shielded is near about 0 and deshielded is the downfield. This is downfield. Then where is the peaks comes from, which proton are showing where the peaks, like alkyl molecule CH, CH3, CH3, CH2, means those molecules are showing the signals near about 0 to near about 2, 0 to 2, not 0 to actually 0.5 to near about 2. Then attaching carbon to the double bond or ketone function, that showing actually near about the 2.2 to the 3. Then when halogen atom are attached to the carbon atom, and that carbon attached to proton, and that halogens, the range of that is near about 3.2 to 4.7 like that. And when there is a attached hydrogen attached on OH or NH, there is a brown means there are the covered long regions near about 1.5 to near about 5.5. Then alkyne, the alkynic hydrogen like this hydrogen is showing the range near about the 4.6 to near about 6.98. Okay, then aromatic compounds, it is a once again downfielded because of aromaticity, and the proton shifted towards near about 6.78 to the 8.5 like that. Then from this also deshaded proton from ketones, not ketone actually, aldehydes. The proton is near about shaded about 8.9.2 to near about 10. And from this also the as carboxylic acid, it is also once again downfielded, or it is the highest downfielded carboxylic acid is peak showing near about 10.5 to the near about 12. These are the how to we know which carbon is there, which proton, which environment of that carbon and that proton we are determined from this range. There is a one in NMR spectrometer. There are using one chemical, that is a tetramethylsilane TMS. It is a reference for this chemical used for the reference, and that peaks arising that tetramethylsilane tetramethyl TMS, it's showing near about 0, and we are using that for the reference. And from setting this TMS to 0, then the peaks where are the comes, then you will see the peaks, other peaks are where come. It chemical shift shows exactly 0 delta ppm in both NMR. Because of that it used as a reference. This compound used in each sample, means whatever we are taking sample at a time in the solvent, it is presence. Because of low electronegativity of TMS, it is a greater than in most other organic compounds. Means because of that it's showing the signals near about